So let's move to the next speaker, which is Professor Gianmarco Griffini. He's an associate professor of material science and technology at the Department of Chemistry, Materials and Chemical Engineering, Giulio Natta of Politecnico di Milano. His research interests are mainly focused on the design, synthesis, and characterization of polymer-based materials and on the study of their structure-property relationships. Areas of major effort include bio-derived and biodegradable polymers and composites for sustainable manufacturing and circular economy, materials and devices for solar energy harvesting, management and conversion, and for energy storage. Stimuli-responsive polymeric materials for smart, advanced manufacturing. In these areas, he has been involved or is being involved as scientific coordinator in several regional, national, and European funded projects, and as responsible for different research contracts with private sector. He currently serves as editorial board member of the journal Aggregate from Wiley. Hi, welcome.
Hello.
So please, yes, thank you once again for accepting this invitation, and please go ahead to start your presentation. Thank you.
Can you just confirm you can see my screen?
Yes, we can see.
Like
perfectly.
Full screen, yeah? And I guess the pointer. Okay. So good morning, everyone, and thanks a lot for the invitation. I'm very sorry not to be able to be there, but due to teaching activities, I couldn't move today. So because of the, let's say, of the topic of the REDONDO project, which deals with basically reversible cross-linking strategies on polyethylene, I'd like to give you a short overview of what we have been doing in recyclable-by-design polymers and composites in the past few years. We will mainly discuss epoxy-based systems, although we will also see one example of a different kind of material, and we will mainly focus on composites. So before getting into the, let's say, the core of the presentation, let me just spend a couple of words on our university and department. So I come from Politecnico di Milano, which is in the north of Italy. And more specifically, the department I'm affiliated with is the Department of Chemistry, Materials and Chemical Engineering, named after Giulio Natta. Our work in our lab is basically focused on the design, development, and testing of advanced polymeric materials for a variety of applications. We mainly do macro chemistry, we do surface modification and characterization, we do polymer processing, and of course we deal with the vast array of chemical, physical, functional, and structural characterization techniques for the materials we produce. Since a few years now, we have been looking into also the end-of-life management of the polymers and composites we work with a variety of techniques, including solvolysis, pyrolysis, and more advanced techniques that I will not have time to talk about today, but I mean, if you're interested, please get back in touch with me. So those activities are mainly focused on one key theme, which I believe well aligns with the main topic of the REDONDO project, which is the circular economy of materials and technologies in general terms. So as Carla was saying, we work on different topics. Today, we will mainly focus on the field of composites, simply because we know that how important they are. Because mainly, I mean, it is also a sort of a lateral, let's say, a parallel line with the main topic of REDONDO, and we know that composites are mostly employed in high-value, high-end applications. We want to have both thermal and mechanical properties while ensuring lightness of the components. So when we talk about composites, and more specifically when we talk about the main chemical classes of structural composites, which are those I will mainly focus on today, we typically work with three main classes. So we talk about unsaturated polyesters that are usually cross-linked with the reactive diluent styrene in order to obtain a three-dimensional network where we have the beneficial properties of thermosets and processability as well. Then we have vinyl ester resins, which are very much used in a variety of applications, certainly for coatings, but also in some cases in wind blades, wind turbines, and so on and so forth. And then we have, of course, epoxy resins. Epoxy resins, which, as you know, can be reacted or cross-linked with an amine, a cross-linker, or with anhydride or acids, let's say. Those lead to different polymeric networks that have specific characteristics and specific, let's say, advantages and disadvantages. In all cases, when we talk about thermosets for composites, of course, we want to look into covalently cross-linked materials that have excellent chemical resistance, they have excellent thermal resistance, reduce creep, and also they can provide the mechanical response that we want, combined with the addition of reinforcing fibers. As we know, the problems there are basically what Professor Bicchiari said. So they're not processable, they're not recyclable, they're not repairable. And these are, of course, issues when we think about the end of life of those materials. So, of course, the point there would be to increase the chances of making those materials more circular by designing systems that can be, let me say, recyclable by design, but let me also extend this to reusable, remanufacturable, repairable by design. In general term, circular. This means that we can increase the sustainability of the systems on the one hand, but also improve, in a way, the market penetration of those materials, because we extend their service lifetime, we increase the value of the material itself, and we can, in principle, reduce maintenance costs and replacement costs. So these are, let's say, this is the background of the main rationale, let's say, of what we have been working on in the past few years. And today I'd like to give you again a general overview of our activities on the design of sustainable resins that can be used for composites, relying on the ability of introducing reversible crosslinks into the matrix, the network, to obtain temperature-assisted reuse, repair, and recycling, but still keeping sufficient thermal stability and suitable processability to use those resins in the field of fiber-reinforced composites materials. So as I would say most of you know, or many of you know, we have several strategies to address these issues. One is certainly to rely on the definition or on the design and development of dynamic polymer matrices. As we know, those systems are basically focused on the introduction of reversible bonds into the polymeric network, and this can lead to the formation of different type of networks. Let's say, on the one hand, we have what we call the associative systems, where we have a sort of a permanent cross-linked network that can undergo bond shifting or bond exchanges during thermal treatment, typically in the presence or in the absence of catalysts. And this enables macromolecular movement that lead then to the possibility of reprocessing the material. On the other hand, we have dissociative networks where we introduce, again, reversible bonds, covalent bonds that can lead in a certain range of temperatures the breakage of the bond, let's say, then the material can behave as a sort of a thermoplastic system, and then upon cooling, the material can recover the three-dimensional structure typical of cross-linked materials, and then again during this heating and cooling, we get to the conditions where the macromolecules can actually flow, and we can get again reprocessing, recycling, and repairing. In both cases, we lead to a polymer network that can actually move in certain process conditions, and ultimately lead to, let's say, circularity of the polymer network itself. Today, I would like to give you a few examples of both cases, starting with the first, with the dissociative systems, and more specifically, looking into what also Professor Bicchiaris mentioned earlier on, the Disolder cycle addition reaction applied to epoxy systems. So, as we know, the Disolder reaction relies on the formation of a so-called Disolder adduct that is formed upon reaction between usually a diene and dienophile. The most common couple used in these cases is the furan-maleimide couple. We obtain this sort of a duct, and this, upon heating and cooling, can lead to the reversibility of the reaction, going back to the original constituents, or getting back to the actual cross-link or to the actual Disolder adduct. It's a very straightforward strategies relying on basically on click chemistry, so it is highly efficient, highly selective, let's say. In our case, what we did was to simply functionalize some epoxy precursors with furan-bearing units in order to make them basically reactive with maleimides. By combining these systems with a functional aromatic bismaleimide, we could obtain, upon heating and cooling, a three-dimensional network that is at the end an epoxy system that could be used theoretically as a reversible material for the incorporation of fibers, for instance, or reinforcing fibers. Of course, the first point to look into is the reversibility of the system, which means thermal reversibility. This was verified through differential scanning calorimetry, and you see here the reversibility is indicated by the presence of an endothermic peak at relatively moderate temperature, let me say. Let me also stress on the fact that upon successive cooling and heating, there is a sort of a fatigue, chemical fatigue, due to the presence, due to the formation of irreversible bonds that lead to a reduction of the endothermicity, which is essentially intrinsic of these type of materials. Then we also checked macroscopically the reprocessability of the systems by solubility tests, and you see that by by heating up the system into a good solvent for the precursors, then we have full solubility of the material, and then if you cool down, we have a full gelification of the material, meaning that the reversibility of the duct is actually verified. And we also reprocess the system by heating up in a hot press, and we could consolidate the material and obtain again a fully cross-linked system. Given these properties, we then decided to incorporate that resin as a, let's say, impregnating resin for a 1 or 2 layer composite material to demonstrate the feasibility of the concept. Once the material was obtained, we evaluated the possibility of recycling the material itself, so dissolve the resin at high temperature, recover the fibers, and potentially reuse the matrix itself. So you see here that the solution was successful. We obtained clean fibers after recovering and cleaning up and washing steps, and the organic fraction was used to deposit a coating that could be used potentially as corrosion resistant or corrosion protection coating, which is also self-healable. You see here a scratch that was produced on the surface of the coating, and upon heating and cooling down, we could obtain a complete healing of the cut itself. So moving on to the second approach, the so-called associative systems, which mainly rely on the Vitrimer chemistry. Here, our activities have been recently focused on the development of bio-based systems. And again, focusing on epoxy resins, the typical epoxy systems are obtained starting from bisphenol A derivative, epoxy derivative, and typically fossil-based acids or anhydrides when we talk about the anhydride cured epoxy system. So what we did there was to, first of all, focus on the anhydride or the acid cross-linker by substituting conventional ones with FDCA, furandic carboxylic acid. By developing this system and by modulating the formulation, we could obtain a three-dimensional network that is actually a fully cross-linked epoxy system. And through the introduction of a transesterification catalyst, triaza-bicyclodecyne, we could potentially envisage their reversibility thanks to the transesterification reactions that can occur at relatively moderate temperatures, let's say. So by, again, modulating the formulation, we could tune the glass transition temperature, which means tuning the operating window in terms of temperatures for those materials. And then we also studied the stress relaxation processes at temperatures higher than the glass transition temperature. And you see that we have relatively good relaxation for all the systems, which pretty well fits the maximum model with relaxation times that are in line with typical systems based on analogous precursors. Then, in terms of let's say functional response, we evaluated the repairability, reusability, and recyclability of those systems. You see that in all three cases we obtain pretty good results. The material can be easily repaired upon scratch and heating. It can be thermoformed after cross-linking, and it can also be recycled by hot pressing. And the material itself, the recycled material, was also tested before and after the recycling process, and you see that we retain most of the mechanical properties with a little bit of decrease of elongation, break, and strain, ultimate strain. Now, this was, let's say, the first step towards a fully bio-based system, which we then tackled by also substituting the bisphenol A epoxy derivative with an algae-based epoxy system, PHTE, for glucerone-based. Again, using FDCA as a co-monomer, we obtain a three-dimensional network that was also additionally formulated with a reactive diluent to make the system a little bit more processable and more easily, let's say, usable as a resin for composites. We included a catalytic system to, again, promote transesterification reactions, which were then evaluated on the cross-linked material. So the material, again, could achieve glass transition temperatures and mechanical properties, which are aligned with typical epoxy-based systems for reinforced composites. We, by modulating the amount of reactive diluent, we could obtain a significant reduction of the viscosity compared with the previous system, which is also good for processability in fiber-reinforced composites. And also, all the materials exhibited very good thermoxidative stability, which was found to increase by increasing the cross-linking network, let's say. Stress relaxation was found for all systems. Irrespective of the amount of reactive diluent, what we saw is that by varying viscosity versus relaxation times, the presence of irreversible bonds could somehow be introduced into the system, and this led to a reduction of the. Oh, could you please? Okay. Switch off the mic, thank you. The time, or increase the time, the relaxation times. In any case, we could achieve successful temperature-assisted reshaping, as well as catalyst-assisted recycling, so a solvolysis process that was also studied in this case to achieve full dissolution. Now, moving to the last system I would like to discuss with you, so the area of saturated polyesters, which is also a pretty large market sector, especially for glass fiber reinforced composites. As you know, in this case, the main problem is the use of styrene as a reactive diluent to obtain the three-dimensional network, cross-linked network. This is needed to obtain the properties that these materials have. The problem with this system is that it is not recyclable. It's not easily recyclable. So what we did was to somehow revisit the concept of unsaturated polyesters by redesigning the material and going towards the use of vinyl ester resins that could be cross-linked with, again, with a methacrylate, hydroxylated reactive diluent in order to provide, after cross-linking, the possibility of having again, a three-dimensional reversible system based on the vitrimeric chemistry through transesterification reactions. So again, we modulated the formulation to obtain different reactive diluent to vinyl ester ratios, and by assessing the thermomechanical response, we also obtain glass transition temperatures which are aligned with what we typically observe on cross-linked unsaturated polyesters, with viscosities which are pretty good in terms of processability. So we could achieve values as low as 0. Let's say 10 to the minus 2 Pascal per second, which are in line with typical viscosities needed for the production of composites through, for instance, infusion. We demonstrated the successful reshapability after curing of those materials. And again, we could obtain full dissolution of those materials in the presence of a suitable catalyst. As I said, one important point of the use or the development of resins for composites is their processability through industrially relevant technologies, let's say. In our case, we focused on the infusion, which is typically the technology for obtaining fiber-enforced composites. And by, again, modulating the viscosity through formulation, we could obtain a very good flowability of our resin, as you can see from the video reported here. This is some of our people working in the lab on composites, and you see that the actual fiber mat can actually be very well wetted by the introduction of the resin through vacuum-assisted infusion. So to conclude, I hope I have given you a good overview of the activities we have done in the past few years on the development of dynamic polymer matrices. Of course, the activities are not, only focused on these systems. We are still working a lot on the development of bio-based networks, focused on composites, focused on coatings. This is certainly a way to go for in my opinion, for the circularity of composite materials. And I'll be happy to answer any questions if you have. Thank you very much for your attention.
Question. I don't know if you hear me, Gianmarco.
Gianmarco is Elena.
Yes.
Nice to...
Hi, Elena. Hi, Dimitris.
Marco, you hear me?
Yeah.
Okay. So, are you considering doing these recyclability and reversibility tests with contaminated samples? Because I'm not a chemist, and from what I see, one of the things that jeopardize many times recyclability is that the materials are not as clean as in lab conditions. So are you considering assessing that not ideal conditions to see how in the end, in reality, it might affect recyclability?
Yes, thanks a lot for the point. It is indeed an important point. So I didn't have much time to discuss this now, but we have been working on recycling of real end-of-life parts in the past few years, and typically composite materials from the wind energy, from the naval sector, from the automotive, all sorts of end-of-life parts. And what we have seen is indeed that the problem of, let's say, complex end-of-life parts is an issue. What we rely upon is let's say, a solid sorting before recycling and after collection of the end of life. This is something that is certainly of importance. And then another point is to develop, in our case, we work on solvolysis, so sufficiently versatile and flexible processes to tackle different type of chemistries. So let's take, for instance, as an example, the wind energy sector. If you take a wind blade, you know that the wind blade is not made of one single material. You have maybe 4 or 5 different materials there. In most cases, we have cross-linked systems. We have been working on these mixed end-of-life parts in the field of solvolysis, and we are developing a process that can actually lead to full dissolution and recovery of the reinforcing elements, the fibers, and also recovery of an organic fraction that can be reused. For instance, as I showed before, as a coating, as a protective coating.
Thank you.
Thank you, Gianmarco. Any other question? No, thank you very much, Gianmarco, for accepting our invitation. Gianmarco is a very good collaborator. We used to work together in MyOMAC project, and we have done very good work in press presentation, Gianmarco.
Thank you very much.
And just to say that Gianmarco comes from Politecnico Milano, NATA's laboratory. Nata and Ziegler shared in 1963, I think, Gianmarco, the Nobel Prize in Chemistry, because they discovered Ziegler-Natta catalysts for high-density polyethylene production. Before that, it was not possible to produce high density. We were able to produce only low-density polyethylene. Just a question from my side, Gianmarco. Okay, Vitrimers is an alternative solution to produce reversible cross-link materials. Do you see any advantages or disadvantages compared with DS-Alder reactions?
That's a very good point. Thank you again. In my view, but again, it's just a personal view, I see DS-Alder a little bit more useful for recycling, so for dissolution. While in the case of Vitrimers, I think the favorable point they have is that they can be thermoformed after cross-linking. So I think that the good advantage of Vitrimers is to make the material reusable rather than recyclable, if you know what I mean. While in the case of DS-Alder, I would say that it's easier, given also the rheological profile you get after heating up. It's easier to dissolve them. So if you want to, my opinion, I mean, if you want to get something, a resin that enables you to recover the fibers very well, probably DS-Alder is better than Vitrimers. This is my, my take on this.
Okay, thank you very much, Gianmarco. If we want to extend the life of this REDONDO project, maybe we can include also another option with Vitrimers. Thank you very much again.
Thank you. Bye-bye.